This video discusses the higher order derivatives, which means we're going to differentiate a given function more than once. Let's say we have a function given as y equals f of x. Let's assume that this function is differentiable more than once. For example, if you have y equals f of x to be x squared, you differentiate it once, you get 2x. You can differentiate it again, then you get a 2. In fact, you can differentiate that also again, then you get a 0. Even after it being equal to 0, you can still keep differentiating and we keep getting zeros. But there are some other cases where you can keep differentiating a function multiple times still without getting a 0. For example, consider sin x. If you differentiate sin x once, you get cosine x. You differentiate it again, you get a negative sin x. Likewise, you can keep differentiating that kind of a function even infinite number of times. In fact, such functions are called infinitely differentiable functions. Anyways, we will now consider a function y equals f of x, which is just differentiable more than once. If I differentiate this function, we can of course write this function as dy by dx. Since y is equal to f of x, we can write this as d by dx. Y can be replaced by f of x. Also, in the past, we've seen the other symbols that are used for these things. D by dx f of x can also be written as f prime x. To be consistent with that, dy by dx can be also written as y prime. We will just focus on this middle part for now. And we will now assume that we are going to differentiate this f of x for a second time. If I need to differentiate that function for a second time, just think about this part. If I'm going to differentiate that part, it will be d by dx. Let me write down this middle part as it is. It's going to be dy by dx. Rather than writing it that way, we have a shorter form to write it. Right here I have a d and it has to be multiplied by another dy. Therefore, that numerator can be written as d squared y. The denominator is dx times another dx, which can be written as dx squared. So, when you go for a second derivative of the function y, the standard way to write it is d squared y over dx squared. Please note that you should never write this square next to y. That second derivative should be indicated right after d on the numerator. In the denominator, it has to be written as dx, after that the squared symbol. Therefore, let me write down the second derivative as d squared y over dx squared. Since y is also equal to f of x, we can write that down as d squared f of x divided by dx squared. The other notations available are, you can write it as f double prime x, which can also be given as y double prime. Let's now assume that f of x is differentiable even 3 times. That means if I have to differentiate the second derivative, how would you write it? D by dx, the second derivative, which is d squared y over dx squared. This is going to be equal to, if I look at the numerator, I have to multiply d by d squared y. Therefore, it can be written as d cubed y over, in the bottom, I have dx times dx squared. Therefore, I should write it as dx cubed. Therefore, let me write down the third derivative as d cubed y over dx cubed. Since y is equal to f of x, the same statement can be written as d cubed f of x divided by dx cubed. Just to be consistent with the previous symbols, we can also write down this as f triple prime x. And the same way, we can write this down as y triple prime. Likewise, we can keep on differentiating a function f of x which is multiple times differentiable. Let's say this given f of x is differentiable n times. If it is differentiable n times, how do you write down the nth derivative? The nth derivative can be written as d n y over dxn. Since y is equal to f of x, we can write this down as d n f of x divided by dxn. To be consistent with these notations, we can write it as this way. F of, we write the nth derivative within parentheses as a superscript x. The parentheses are required, otherwise we might be misleading somebody who is reading this thing as f of x is raised to the nth power rather than f of x is differentiated n times. The same way we can write down y also as y superscript within parentheses n. Please note that we can write down first, second, third, so on derivatives also the same way. That means this first derivative, if necessary, can be written as f within parentheses superscript 1 x. Similarly, that y prime can be written as y superscript within parentheses 1. The second derivative can be written as f superscript 2 x. Similarly, y double prime can be written as y superscript 2. The third derivative can be written as f superscript 3 x. Similarly, this can be written as y superscript 3. All right. Now we will look at an example. Here's your first example. We will let y be sin x. Obtain d fourth y over dx fourth. I need the fourth derivative. We have to go step by step. Since y is equal to sin x, let me differentiate that once. Hence, I can obtain dy by dx. dy by dx should be equal to cosine x. By differentiating that first derivative one more time, we can obtain the second derivative, which we can write as d squared y over dx squared. Cosine x differentiation is equal to negative sin x. By differentiating that second derivative again, we can obtain the third derivative. The third derivative, d cubed y over dx cubed, should be equal to negative times the derivative of sin x. Since the derivative of sin x is equal to cosine x, with the negative symbol right here, we're going to write down the answer as negative cosine x. Now we can differentiate the third derivative again in order to obtain the fourth derivative. So the fourth derivative is d fourth y over dx fourth. This is going to be equal to the negative symbol times the derivative of cosine x. Since the derivative of cosine x is equal to negative sin x, with the negative symbol right here, it becomes a positive sin x term, because negative times negative is positive. Therefore, let me write down the fourth derivative as positive sin x. In fact, we have obtained the originally given function itself after the fourth differentiation. This is the answer for that problem. We will look at another example. Here is your example number 2. This example is given to you with a specific message. All the rules of differentiation should be strictly applied when you go for higher order derivatives as well. There is no exception. For example, if there is a product of two functions of x, please make sure to apply the product rule. If there is a quotient of two functions of x, please make sure to apply the quotient rule, and so on. So here's your next example. We will let y be x times cosine x plus 3 sin x. Find d squared y over dx squared. I need the second derivative of y. Let's first find the first derivative, which is dy by dx. When I need to find dy by dx, first I have to differentiate x cosine x part. It's a product of two functions of x, which means I must use the product rule of differentiation. So what's the product rule of differentiation? The product rule of differentiation is, if I have f times g to be differentiated, the derivative of f times g is equal to f times g prime plus f prime times g, where f prime and g prime are the first derivatives of f and g respectively. I have proved this result using the first principles. Therefore, I'm going to go ahead and directly apply that result in order to differentiate that first part of the y. Therefore, I will take this x as the function f and cosine x as the function g. The derivative should be therefore equal to x times the differentiation of cosine x is negative sine x. Let me write down that negative symbol here, sine x, plus cosine x times the derivative of x, which is equal to 1. Cosine x times 1 is just cosine x, therefore I will just not write a 1. Now we are done with that first part, but this function has another part, which is right here, 3 sine x. There's this positive symbol, therefore let me go ahead and write that down. How do you differentiate 3 sine x? Do you have to use the product rule for that? Because it is 3 times sine x? We do not need to use the product rule. We may still use the product rule, but it's going to be redundant. It will be a waste of time, because according to the second property of differentiation, you can factor out any constants and differentiate rest of the function. Since 3 is a constant, I'm going to factor that out and simply differentiate the sine x term. Sine x differentiation is equal to cosine x. Of course, I need to go for the second derivative. However, the first derivative can be simplified more. dy by dx. Of course, the first term is by itself only negative x times sine x, plus these two terms, cosine x and 3 cosine x, can be simplified. They will be added to become a 4 cosine x. Now we can go for the second derivative. If I differentiate both sides one more time, we get the second derivative of y with respect to x to be equal to, right here I have a negative symbol. It's just like a negative 1, which I'm going to factor out. And let me open brackets, and now I need to differentiate x times sine x. Once again, I have to apply the product rule. When I apply the product rule and differentiate it, it's going to be x times the derivative of sine x, which is cosine x, plus sine x times the derivative of x, which is equal to 1. Sine x times 1 is just sine x, therefore I will just not write 1. Close brackets. And then I have this plus sign right here. However, when I differentiate 4 times cosine x, since the derivative of cosine x is equal to negative sine x, that plus sign can be simply replaced by the negative symbol and write it as 4 sine x. Now we can simplify the second derivative of y and keep our final answer. D squared y over dx squared should be equal to, I need to distribute this negative symbol into each of these two terms within brackets. When I do so, I have negative x times cosine x minus sine x, and I have minus 4 sine x remaining outside, which will be simplified to become minus 5 sine x. That's the answer for this problem. All right, I think that should suffice about an introduction to higher order derivatives. Thank you so much.